All right, back from break. In the earlier part, we took a look at these problems, which was, it was a midterm 1 from previous semester. Let's take a look at another set of problems. So here's another midterm. Again, 4 problems, 1, 2, 3, 4, with subparts A, B, C, D. Ooh, look, there's an E. So anyway, that's going to be the format for the midterm coming up. Now, on this set of problems, problem 1 actually is 2-dimensional. This is a baseball being hit at 40 degrees, initial velocity of 35 meters per second. Okay, so kind of the standard sort of questions. How far does the projectile, this is projectile motion, how far does the projectile travel, how high does the projectile go, and will the projectile make it over the fence so that it's a home run? All right, I drew a picture. Did they ask me to? Nah, but I drew one anyway. So here's my diagram, and when we were looking at projectile motion, we kind of set this out. Point A, where we're launching from, point B at the maximum height, point C. And you know, you can pick whichever points and label them whatever's convenient for you, but that helps me to focus on those particular points. So part A is saying how far does it travel if it comes back down and hits the ground. So assuming everything is level here, then that's just a distance d. So I wrote down the given information, 35 meters per second to start with, initial angle, 40 degrees, and then we're going to set up a coordinate system. It seems easiest to set up a coordinate system where point A is at the origin. X naught equals 0, Y naught equals 0. That's easy enough, and there's no reason not to designate these values as being at the origin. Now, if I'm going to get distance downrange, I need 2 things. I need to know 2 things. I need to know how fast are we moving downrange. Now, the x velocity that we start with is going to be v naught cosine theta. So the distance we travel will be v naught cosine theta. That's exclusively the x component of the velocity, and that's going to remain constant. Remember, in projectile motion, the acceleration is only in the vertical. That's where the gravity is. The horizontal motion we treat as constant velocity. Again, neglecting air resistance. So it depends on how fast we're traveling in the x direction, and it depends on how much time we travel. Now, the time is going to be related to vertical information. The amount of time that it stays in the air depends on how much vertical velocity we launch it with. So I think we'd said that this is kind of a compromise between I want it going downrange as fast as possible, but I want it to stay in the air as long as possible. And so I've got to look at x formulas and y formulas. The y formulas, which I have right here, this is y, the vertical direction, as a function of time. Now, at point C, y is equal to 0. So y is equal to 0, well, y naught was equal to 0 too. So that goes away, and that all goes away. So if those disappear, I just have to set these 2 terms equal to each other. This minus 1/2 gt squared, that's the acceleration effect due to Earth's gravitational field, and that's bringing the object back down. So this is, as time goes on, the initial velocity upwards is giving it an upwards boost, but gravity is bringing it back down to Earth. So I set those 2 terms equal to each other, because these are 0, and solve for t. So one factor of t goes away. T then is equal to 2 v naught sine theta over g, and at that point, I plugged numbers in. I went ahead and plugged some numbers in. I was curious, and so it worked out 4.59 seconds. So there was enough vertical velocity that we launched with in order to keep the object in the air for 4.59 seconds. Now, what I did then is I took this formula, not the number, but I went ahead and took the formula and plugged it in for t. So when I'm at point C, when the object, the baseball, lands back down on the ground, this much time has passed. I plug that in, and what I'm finding is at point C, the distance I have traveled, this is now little d, is v naught squared over g 2 sine theta cosine theta. Now, if you remember in class when we introduced this, we said there is a trig identity that says 2 sine theta cosine theta is the same thing as sine 2 theta. So I swapped that out. That makes it a little easier to work with if I have sine 2 theta. So putting those numbers in for the initial velocity, the angle. Now this is 2 theta, so if theta is 40 degrees, 2 theta is 80. And putting those numbers in, it says that the total distance downrange that this baseball will travel, assuming a level playing field, is 123 meters. That's the distance that it will travel. That's little d that we have here. Now in part B, it says, what's the maximum height reached by the baseball? So for height, now I've identified that as h right here. What I could do is go back and use a different formula. I don't really have to work in terms of time. I can work exclusively in terms of distances, in terms of h, by using v squared in the y direction is equal to v naught squared in the y direction minus 2gh. Now remember, in the vertical direction we have constant acceleration, in the horizontal direction we have constant velocity. Don't get the acceleration problems mixed up. There is no acceleration taking place in the x direction. You know, I cannot use formulas of acceleration to determine what's going on in the x, but I can in the y. And so in the y direction, let's see, when I get to point B, the velocity in the y direction has gone to 0. It's momentarily 0 at that point, so I can set that equal to 0, solve for h, and it says the maximum height reached by a projectile is given by v naught squared sine squared theta over 2g. So I've plugged that in here, and that gave me, plugging in all the numbers, canceling out all the units. I've got units of meters, and the numerical value 25.8. So it's going to reach a maximum height of 25.8 meters. Okay, so I'm carefully selecting the formulas of constant acceleration and the formulas for constant velocity in the x. Finally, in part C, it says, okay, we're in a baseball field, there's a center field fence, and it's 110 meters from where the ball was hit. So, and this person, when they hit the ball, they really went down in the dirt to hit it. They hit it right at ground level. So this is a remarkable hit. They hit it so low, but were able to bring it up high enough that it launched at 40 degrees. A remarkable, effort. So in part C, what we can do then is we can go downrange 110 meters and find out how high it is at that point. So in part C, this is now the x value I want to work from, and this I want to compare with the y value. So let's try that. Taking the same formula we used here, now what I can do is solve for time. How much time is it going to take to travel 110 meters downrange? And so 110 meters downrange, I put in the velocity and the angle, the initial velocity. It says it's going to take 4.10 seconds. Okay, so it's kind of interesting. So it took 4.59 to get all the way to here, and that was 123 meters. But there's a fence, right there, There's a fence. It's 110 meters down range. And it's going to take 4.10 seconds to reach this point right here. Now the question is, when I get to that point right there, that's 110 meters in the x direction, what's the y coordinate? And I can go back to the y formula. So I can come back to this formula. Now y not 0, so that's dropped out. And then I plug numbers in and put in 4.10 seconds, and it says at that x value, the corresponding y value is still 9.8 meters. So it's still a good distance above the field. It's going to go over that 5-meter fence. 9.8 meters is bigger than 5.0 meters. Yes, it's a home run. All of the A's fans stand up and cheer. A leadoff home run. Okay, questions on any of this? This is projectile motion. It's coming from chapter 3. If you go back and look at chapter 3, that's where we started looking at 2 dimensions at a time. So we're looking at motion in the x and y together. And then this is a good example. So again, I think these examples we're looking at are all very relevant. Ooh, let's see. Problem 2, not only do we have sliding blocks, but we have friction. So this is a, to me it looks like a fairly challenging chapter 5 problem. So we have friction going on. What we're going to have to do, and we have 2 different inclines with 2 different angles. I think there was a homework problem like this that we looked at. In any case, I've got my diagram. I've got the forces identified for each of these objects. Now I'm going to do that whether or not the problem asks for it. It does turn out that I get points for this. Force diagram, draw those free body diagrams or force diagrams for each of the blocks. And so now I labeled this one as M1 and this is M2. And what I've done in this force diagram, I think all the ones that we're going to be looking at, is I have gone ahead and divided the gravitational force into components, just up front, figuring since we're on an incline, there is going to be a sine theta component and a cosine theta component for the gravitational force for object 2. I drew those. And then I got the gravitational components for object 1 also. And I got to make sure I get the cosines and sines correct. So, and then N1, there's a normal force here, and N2, there's a normal force here. Now the tensions are the same. Remember, the pulleys so far are massless. There's no friction in the hub. There is friction along the circumference. So as the string goes by, or the cable goes by, the pulley does rotate. But since the mass is so small, we don't have to include its effect. Now, since there's friction, we've got to take a closer look at the frictional forces. And the frictional forces are here, F1, F2. Now, these are both kinetic friction. We're told that the system is sliding to the right, and so there's a velocity up there. Now, something that's very, very important in the problem is we're told that the velocity is constant, okay? And this problem has so much stuff going on. I'm kind of really happy that the velocity is constant, because if the velocity is constant, that means there is no acceleration, and that means that my formulas for the forces will simplify. If this is moving at a constant velocity, what I can do for object 1 is say that looking at object 1, now tension is in the forward direction, M1G sine theta 1 and F1, the frictional force, are in the opposite direction. I can set those equal. So if tension were larger, there would be an acceleration. But there is no acceleration, so the tension must be the same amount of force. So the forces in the forward direction equal the forces in the backwards direction for object 1. Now what I can also see is N1 is equal to M1G cosine theta 1. Now I use that because of the frictional forces. I have a frictional force, I am given a coefficient of friction. That means that N1 does come into the problem. And so the N1 is now going to be substituted with M1G cosine theta 1. The formula for the friction on object 2 looks the very same. So the two frictional forces I have to step through. First of all, it's the coefficient times the normal force. And I'm going to say don't skip steps here. You know, you guys are learning this stuff, you're practicing these formulas. Stop and talk yourself through these couple of steps. If you have something like this in your notes and you just copy it down and you're not thinking about it, it may get you through the problem this time, but you're not building that intuition about why. Why does this formula work? So again, don't skip steps is going to be my advice. Do this step first and then take the ends, look back at the diagram and go, yeah, n equals mg cosine theta. All right, so this formula applies to object 1. Now object 2 is not accelerating either, so the gravitational force here is going to be the same value as tension plus the frictional force. Now what I was able to do then is take the tension expression, substitute that in. It says that m2g sine theta 2 is going to need to be as large as m1g sine theta 1 plus the two frictional forces. There needs to be a large enough gravitational component down the incline on the right side. This needs to have a large enough gravitational component to offset this one, and that's a steeper angle, and offset the friction here and offset the friction here. So I'm guessing that's got to have a lot more mass. It does not have a steep angle to work with, and it's got to offset two frictional forces. So again, do the algebra, stare at the formulas, and see what it's telling us. Now, I think at this point we have all the numbers, right? Let's see. The mu's are both 0.18. So, and then the mass, we have mass 1, but we don't have mass 2. And so that's actually what we want to calculate next. So we got those force diagrams drawn. All the forces are in place. Now let's solve this expression for M2. M2 is in this term. M2 is also here. So that term needs to get brought over. And I did that, and I factored out the common factor of M2. So algebra, right, on all these problems. We're always doing a lot of algebra. Now what I hope you guys are finding out is that there are certain algebraic manipulations that become very common. So it's very common to get factor formulas set up. Both the M1s are on this side, but the M2s are split. I got to bring the M2 factor over, factor out the M2. And meanwhile, I combine the factors on this side. And so what I ended up with was this formula. Now I now can divide through by this, and then I started putting the numbers in. And what I got for M2 was 10.2 kilograms. That is a lot more than M1. So I'm thinking that probably is a reasonable number. In part C, it says find out how much tension we've got. Now again, since the pulleys are still massless, the tensions are going to be the same on both sides. I'm not solving for two numbers, I'm just solving for one. And if I come back to here, for example, I can solve for the tension using this formula. I can also solve for the tension using this formula. So that's what I did. I came back and solve for the two tensions. And putting all the values in, this became tension. So I had to substitute in the F1. I didn't solve for that individually. And then I had to solve in the, substitute in the F2 for this one. I solved for the two tensions, and they did work out to be the same number. So that's encouraging. It's not a guarantee that we've done it right, but it certainly is encouraging that it's looking like we may have gotten through the problem and done things correctly. So that's good to know. All right. So you can see we're asking for kind of the same stuff. Velocities, accelerations, tensions. This one was a little different in that we actually solved for the mass. But in any case, the formulas start to look kind of familiar, and that's why you practice these problems over and over. You do them once, and then you go back and kind of talk yourself through it again. Each time you go through the problems, make sure you're thinking about why each step. Why is it this step? Don't try and memorize just a bunch of formulas without having meaning behind those formulas. Why do the formulas look like they do? All right, let's take a look at that third problem. So, what did we have here? This is like chapter 3, this is like chapter 5. Here on problem 3 we have another automobile. This time it's going around a curve. So it's not putting on the brakes like in the last example. This time it's going around a curve. It's going at a constant 50 kilometers per hour. The curve has a radius of 60 meters. Now, you may think 60 meters sounds pretty large, but if you're going really fast, that's a fairly tight curve that we have. Now, once again, it says draw a diagram showing all the forces. Now, we've looked at these problems in class, and what we have shown is probably the best view is what we call a front view or a back view. I prefer a back view so I don't get run over. And so what I'm looking at is I'm standing on the road, looking at the car, moving away from me. And I can see, here are the tail lights, there's the license plate, there's the rear window. There's a gravitational force on the car. There's a normal force on the car, where the tires are in contact with the pavement. And then, if I'm turning to the right, so I'm assuming I'm turning to the right in this problem, the car's going like this, that means that I'm going to have an acceleration to the right towards the center of the circular motion. And there's nothing in particular located at the center of the circular motion. It's just the center of the circular motion. And that is the direction the acceleration is pointing, and that is the direction that, in this case, the static friction force will be. Now, these are considered centripetal accelerations and centripetal force. The centripetal just means it's directed towards the center of the circular motion. So, so that's it. That's my force diagram. And I'm depending on the static frictional force of the tires to provide the acceleration towards the center. Now, in part B, they are asking us to determine what we know the direction. It's circular motion, we know the direction, so write that down. The acceleration direction is towards the center of the circular motion. And then to calculate the acceleration, I am probably going to be using the formula v squared over r. So v was given in kilometers per hour. Those are not standard units. I got to get that switched into meters per second. Now, one way to do that we've looked at in class, the 50 kilometers is 50,000 meters, and 1 hour is 3,600 seconds. That gives me, for a velocity in standard units, 13.9 meters per second. So 13.9 meters per second is the speed, and that's what? That's going to be like 30 miles an hour or something. So not too terribly fast, but I'm plugging that in and then squaring the velocity, dividing through by the the radius. And again, 60 meters is, well, it's not a super tight curve, but you can see the acceleration here. The acceleration is 3.22 meters per second squared. That's a pretty good amount. It's like 1/3 of a g of acceleration. Now, 3.22 meters per second squared in this direction. In part C, we're coming back and saying, how large is the frictional force that we would need? Now, to calculate how much friction we're going to use, we can start by saying, well, the acceleration is a result of the static frictional force divided through by the mass. Turn that equation around and say, okay, I need this much static friction. I need enough static friction to take a 1,000 kilogram object and accelerate it at 3.22 meters per second squared. So the kilograms times meters per second squared units, those are going to give me newtons, and putting the numbers together gave me, now there's stuff going on in my calculator. I'm rounding as I go along. I rounded a bit here. Here I just went ahead and kept 4 sig figs. So it came out at 3,215 newtons of static friction are going to be needed. Now, the question becomes, am I going to have that much static friction? Are the tires in good condition? What about the pavement? Is it raining? Is it icy? Is my car going to be able to have this much force to accelerate it? So in part, oh, there's D and E, huh? What's the minimum coefficient of friction if we're going to prevent any kind of slipping? So I don't want the car sliding along the pavement. I want to maintain static friction the entire curve. So now the maximum force for static friction is going to be related to the coefficient of static friction times n. Now that's going to be larger or equal. It could be we're right at the limit, right? We're right at the limit where the car's going to start slipping, but probably not. Probably we have a good margin there. So this maximum force is going to be larger than the static force that we're actually using in the problem. Now, the static force we're using is given by m times a. So this will tell me how much static force I'm using, or this will. And so what we can say is, for the car, mu sub s, now n is equal to mg. Those two numbers are the same, so I can take the n out, substitute with mg. This becomes mu sub s mg, and greater than or equal to ma, and the m's cancel. So the m's drop out. Why did that happen? Well, let's take a look and see. If the car has twice as much mass, how much mass did the car have? 1,000 kilograms. What if it's a 2,000 kilogram car? You know, what if it's an enormous car, 2,000 kilograms, much larger? Well, if the m is twice as much, there'll be twice as much gravitational force, and that will pull the car down with twice as much force, and that will put the tires in better contact with the pavement. So making the car heavier makes the normal force go up, and it makes the frictional forces go up. Now we're assuming everything there is, the frictional forces go up proportionally. So certainly the n will still equal mg. That's not in question. And then our model for frictional forces, both static and kinetic, say that as the normal force goes up, so does the frictional forces. And so the masses cancel out, and that reduces down to saying the static coefficient of friction needs to be at least as large as a over g, and that would be 0.33. Now, you know, we said that car tires on pavement have a coefficient of static friction of like 1. So if it's good conditions, if I have good tires on good pavement, not a slippery surface, no ice and snow buildup, then we should have no problem. But if it's icy, then we could have a problem. Okay, the coefficient of static friction on an icy road could easily drop below that 0.33 number. And then in part E, it does say what happens if we use a 2,000 kilogram car, and that was our previous discussion about as the mass goes up, all the forces go up proportionally. So at twice the mass, I'll have twice the gravitational force, twice the normal force, and that will enable or allow for twice as much static friction. The masses cancel out, everything stays the same. I'll still need a coefficient of static friction between the tires and the roadway of 0.328. Questions on any of that? Let's move on to that last problem. So again, chapter 3, chapter 4, good example, 5. This looks like 6. So here we are looking at the planet Mars. Mars has 2 small moons, Phobos and Deimos. It's like, what is it, Fear and something. So this is its moon, Fear, Phobos. They each orbit, this Phobos orbits with a period of 7 hours. So, wow, that's pretty short time. Earth's moon orbits roughly once a month, but this moon orbits at 7 hours. Now that means that this moon must be pretty close to Mars. Our moon is relatively far away. Phobos must be pretty close. The radius of Mars, just for reference, 3,400 kilometers, and the orbit is at 9,400 kilometers. So look at that. Phobos' orbit is only 3 times, and that's a radius, 3 times the radius of Mars. So yeah, it's in a fairly low orbit, this small moon. They're both in fairly small orbits. Let's see. So we want to determine the mass of Mars. So we've seen this before. What we can do is I drew the diagram. They didn't ask me to, but I drew it anyway. I took the period that they gave me, converted that into seconds. 7 hours. So 7.5 hours, and it's orbited. And so several times a day, you could see this moon moving through the sky, and then it disappears on one horizon, and then it shows up on the other horizon a few hours later, makes its way across the sky. That would be fun. And then the distance, center to center, from the center of Mars out to where the moon is, center of the moon, is 9.4 10 to the 6th meters. I brought out the same formulas as before to represent circular motion. And we can either solve for velocities or we can solve for periods. We can use either one of these. So that's the kinematics. Here is the force formula again of the acceleration given by the gravitational force divided by the mass of the moon. And the mass of that small moon cancels out and says the acceleration is due to, big G, it's due to the mass of Mars. So it's the mass of the central object determining what the acceleration will be. And then I divide through by the distance squared. So I'm going to take these formulas again, I guess take the same ones as on the previous midterm one. Set those equal to each other. This time I'm going to take the formula and solve for mass. When I look at that formula, the mass is in there, the orbital radius is in there, the period is in there, I could put the velocity in there, and then we solve for whatever is missing, whatever they want us to solve for. In this case, they have told us the orbital radius, they've told us the period, I can put all of those numbers in, don't forget the factor of 4 pi squared, and I ended up with a mass of Mars that 6.48 10 to the 23 kilograms. Now, Earth has a mass of 6 times 10 to the 24th, So Earth is, more mass by an order of magnitude. Mars is pretty small compared with Earth. So Mars has about 11% of what the Earth's mass is. The Earth is almost 10 times as much mass. Let's see, so we figured out the mass of Mars by looking at that orbital period. Now what they want us to come up with is the velocity and acceleration. So here is Phobos, and the velocity is going to be tangent to the orbital motion. So I'm using the diagram to provide directional information, and yeah, anytime they ask, like in part B it said what's the velocity and acceleration, you need to show a diagram to show what directions they're in. It's one thing to go in and calculate the numbers, which we have done here, but they need the directional information too. Vectors and accelerations, those are vectors. Velocity and acceleration, those are vector quantities, and you need to report both magnitude and direction for those. So they're in my diagram, so I've got that covered. Now the velocity I can get is 2 pi r over t. In fact, that was given, right? I could solve that right from the start. Didn't need the mass of Mars for that. The velocity here is 2145 meters per second. So it's moving, a couple thousand meters per second. And then the acceleration too, I can solve from the given information. V squared over r. So here's the velocity squared. That's meters squared over meters. Leaves me with the meters. And the second squared stays in the denominator. So yeah, that formula works. That is going to give me units of acceleration. So the units here, meters per second squared, and then putting the numbers in, then the amount of acceleration, the magnitude, 0.489 meters per second squared. All right, now that's Mars' gravitational field out here is 0.489 newtons per kilogram. In part C, they say what would the gravitational field be back on the surface of Mars? And for this, I'm going to need that information about the radius of Mars itself. So now if I go back and say, what's the gravitational field here, I'm going to need to get that distance. Now, I was just looking at the scaling on this, and the moon's too far away, right? The radius of the moon's orbit is about 3 times the radius of Mars, and so the orbit would actually be more like in here somewhere, right? I exaggerated how far Phobos is away from Mars. In any case, I came back and used the formula for the gravitational field. Now for R, I want to use R at the surface, and they told me that Mars radius 3.40 10 to the 6th meters. So big G, the mass I do need, I got that calculated in part A. Putting all the numbers in, checking all the units. Now this is a gravitational field. I'm going to keep units of newtons per kilogram. The number on this is 3.74. So compare that with Earth's gravitational field at the surface. Now on Earth, there's more mass. There's like 9 times as much mass. So Earth has like 9 times the mass, but Earth is also bigger. It's spread out. It's not as concentrated. So both effects come into play. If I'm standing on the surface of Mars, I'm closer to all of the material that Mars is made out of compared with when I'm standing on the surface of the Earth. Earth's bigger, the mass is more spread out. And so the bottom line is the gravitational field depends on both. It depends on how much mass is there, and it depends on how compactified the mass is. So for Mars, the gravitational field is definitely less. I mean, it's like 40% of Earth's gravitational field, something like that. Not terribly different, but still, it's less than half. And then finally, on part D, it says there's an astronaut, 65 kilograms on the surface of Mars. What would the gravitational force be? And it's mg. right? We just use Mars' gravitational field instead of Earth's, and the astronaut comes in at 243 newtons. Now, I wanted to do a comparison, you know, what would the force of gravity be on that 65 kilogram person back on Earth? On Earth's surface, it would be 637 newtons, but on Mars, the weight, it's a dangerous term to use, I know, but the gravitational force would be reduced to 243 newtons. Okay, so just for comparison there. All right, well, that takes us through this second set of problems. So again, let's see, this is a review. So our mascot, Laney the Eagle, is here cheering everybody on for the midterm. So if you guys have questions, you know, I've got office hours scheduled, stop by office hours, let's get any questions looked at. You know, good luck with all of your preparations for midterm 1.